Well, hello kitties and curious adults. Here we are with a NOS tutorial. We're going to look at time division multiplexing here. Now it's an advanced subject, but I'm going to stay at a fairly introductory level. Now those of you who purchased my learning package consisting of the SC500 kit, snap circuits, and the digital multimeter, analog multimeter, and the CD with all of the lessons, KT2 lessons, and the extra stuff. This is from the extra stuff that's on that CD. So TDM, time division mux, what is that? How does it work? Well, even though this is introductory, there's some background that you really should have, and that would be understanding what a codec is. Do you know what a codec is? Well, if you don't, I'll show you a little bit about it, but do you really need more information than I'm going to show you here? You also need to have some understanding of data streams, so you might want to go look up some of those tutorials. Alright, here we go. This is from Kidtricity 2, KT2 lesson number 8, page 25. Time division mux, oldest and least complicated serial or sequential way of putting multiple input streams onto a single output path. That's what a mux does. Puts many things onto one thing. In this example I'm showing you here, this is a telephone system. One of the oldest ones there is in digital time division multiplexing. It's known as T-type carrier here in the United States. So what I've done now is take an analog voice input right here, voltage variation coming from a microphone, put it into a codec, a coder decoder, converted it into digital right here, an 8-bit byte representing periodic samples of this voice. Now this is a telephone system that I'm dealing with here. So you need to know a couple of base pieces. The first is that this is always band limited to no more than 4 kilohertz. That's because standard telephone lines always handle the voice at 4 kilohertz or less. So the wizard that figured this out, a guy named Nyquist, says you must sample the incoming analog frequency at least twice the highest rate or highest frequency of that signal. So if we've got a 4 kilohertz max coming in, Nyquist says twice that. The codecs will sample at 8,000 times per second. Each one of the samples then will be turned into an 8-bit digital code representing that sample. I'll show you this in more detail on the next slide. So now I've created an 8-bit sample here every 125 microseconds. I take that 8-bit sample, and this is where the time division multiplexing sequencer comes into play. It takes this 8-bit, puts it out here on this shared facility. Right here's the 8 bits that were this guy's. Then I take the next codec's 8-bit sample and I stick it on the line. Then the next one and I stick it on the line. Now I've only shown 3, but there are really 24 in this T-type carrier system that we're going to be using as our example. So if I'm doing something 8,000 times per second, which I am back here, that means I'm doing it every 125 microseconds. So that's telling you then that out here on the transmission facility, each one of these channels, 24 channels, will gain access to that transmission facility every 125 microseconds. That's the way it works. All right? So think of it this way now. I've got an 8-bit byte that's 25 microseconds long here, but I have to squish it down in time out here so that that 8 bits now occurs in about 5 microseconds rather than 125 microseconds. You okay with that? So effectively I squish the bits down in time so they're much shorter duration of on-off pulses, or volts on, volts off, or high volts or low volts, whatever the system happens to be working on, and that's a little bit too much detail for our little tutorial here. So let's move on to look at a little bit more detail on the codec. So here's my encoding step: sample, quantize, encode. Right? So here's my sample right here. A little window opens up, checks the voltage on the wire from the microphone, brings that little pulse of voltage over to a measuring device, gets a number, takes that number, converts it into an 8-bit code that represents that number. Now normally in the CD that this stuff came from, this slides over here, so you'd be able to see the whole bit stream here, the 8 bits. So that number value here, minus 125 or whatever it was, I can't remember, is coded in this bit sequence right here, 8 bits long. So this is the American T system that we're looking at now. I want to make sure you understand that. So I'm creating now an 8-bit byte right here that represents this instantaneous sample, and there are going to be 8,000 of these samples coming in here. So each one of the 8,000 is measured, and an 8-bit byte is put out for each 8,000 per second sample. So if you do this counting here, you'll find that we have 8 bits per sample, and we have 8,000 samples per second because, right, Nyquist, 8,000 samples per second. So we're going to create a signal known as DS0, digital signal level 0. It's usually called DSO, even though that's a 0. They call it DSO. That's a 64 kilobit signal per channel, right? So the next page will show you the 24 channel or the American T-type system, DS1 serial bit stream, because we're going to interleave 24 of these guys, 24 of these DSOs, or 24 of these 64 kilobit signals, to create what's known as a T-type carrier system. Now, I hate to burst anybody's bubble because I've seen this all over the place, but I've been in the industry since 1961. Started working on T-type carrier systems about 1965. I've worked on hundreds of carrier systems in the telephone company. All of them had letters on them. The earliest ones back from the 1920s and 1930s started with like the letter B and C and like that. I started working on these things when we were working on O, N, N1, N2, N3, K carrier, worked lots of K carrier. All these just had letters. The telephone company, Ma Bell, always named them with a letter. Well, when they finally invented digital carrier systems, time division multiplexing, next letter in the alphabet, oh, hey, let's use the letter T. So it doesn't stand for terrestrial, it doesn't stand for twisted pair, it doesn't stand for any of the other baloney that you see floating around out there. It's just the next letter in the alphabet. So there you go. Sorry to burst your bubble if you thought it was something else. So I've got a digital carrier system, a T-type carrier system. I'm going to do this. I'm going to interleave 24 of the codec outputs and stick them on out here on the line. So I've got 125 microseconds for this 8-bit byte from channel 1 for that single sample, but I've got to squish it down here in time, because if I got 125 here, I don't have 125 for it here, because I got to share it inside that 125 window right here. So here's channel 1, squish down, channel 2, squish down in time, channel 3, blah, 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 like that. So I end up with 24 time slots or channel slots of 8 bits each, which gives me 192 bits. From here to here, 24 channels is 192 bits. But I need to add a frame bit right here, which makes 193 bits per frame or per rotation. Now remember, there are 8,000 rotations per second here, right? So I've got 8,000 frames per second rotations of 193 bits. So 8,000 times, right? 8,000 times 193 bits gives me 1.544 million bits per frame or per rotation. It's also known as a DS1, digital signal level 1. 1.544 million bits in T-type systems is DS1. Right? But I didn't change the bit pattern by squishing it down in time. I just made it shorter in duration. Alright, so here. This one I've been trying to fix for years. You can't do it, so, but I'll point out to you. There is no such thing as high-speed data. The word speed means velocity, how fast something is moving. That doesn't mean this at all. Here's our T-type carrier system. Letter doesn't stand for anything. It's just T. So here's our 24 channel rotations right here, right? This little arm is going to come around here and touch these little buttons. It's going to rotate 8,000 times per second, because that's what Nyquist says you have to do for voice, 4 kHz voice. So here's channel 2. It's the 8 bits from the coder process right here. This arm picks up those 8 bits and sends them out right there on serial. Then it moves to this one, sends out those 8 bits. Then it moves to this one, sends out those 8 bits. So it serializes these 24 channels right here. Our bit rate, remember, was 24 time slots of 8 bits each plus 1 framing bit. That's the red guy right here. Gives us 193 bits per frame. There's 8,000 frames per second, because this is rotating 8,000 times per second. Gives us 1.544 megabit rate. That's the rate of the bits per second. Look at this. This is the E carrier, European carrier. It has 32 time slots, right? You know the computer geeks got involved here because a time slot starts with 0. That's the dumbest thing I ever seen from a hardware perspective. I can't tell you how confusing this gets trying to tell somebody which piece of hardware to go look at, starting counting to 0. Incredibly dumb. But it's okay for computers. Works fine. So we got 32 time slots here, but these 32 time slots of 8 bits each also have to fit within this rotation. This little arm is rotating 8,000 times per second. It's Nyquist. So over here we got 32 time slots times 8 bits equals 256 bits per frame. 8,000 frames per second, same as over here, gives us 2048 megabits. This is the rate, not the speed. These little bits over here are not physically moving down the wire any faster than these. You can't speed them up. You can increase the rate by decreasing the time for any individual bit, but you can't make the bits, the voltage pulses, go faster. Stupid, but you can't fix this, so don't worry about it. Okay, so this now is an exercise for you to go through. We won't have time on my little video right here, but this will allow you to be a digital receiver, a digital demultiplexer, because this is an example of how you can figure out where to start counting a particular set of bits for a particular time slot or channel. So go ahead and work through this. I think it's fairly self-explanatory. I know the kids in the class that I've used this on many times over the years, they figured it out, although it sometimes took them a few times to go back and forth and back and forth. So I'm going to flip through the slides here. Okay, you got that one. You might have to put your video on hold. Draw boxes on a little piece of paper like this. Then do this with that little piece of paper with the boxes you just did. Then do this, and you should be able to figure out where to start counting the framing. Then here is the answer. I'm going to give it to you by counting 1, 2, 3, so you can stop the video to try this. Okay? Alright, here we go. Stop the video at 1, 2, 3. And here's the answers. Okay, I'll see you on the next tutorial.